Ever stop and wonder what really holds our universe together? Well, the answer is hiding in plain sight, deep inside the atom's core. Today, we're going to unlock that secret. We'll follow the story of scientists whose accidental discoveries didn't just change science books, they literally changed the world. Let's dive in. So, let's start with the big question, the one that bugged scientists for decades. What is actually going on inside that tiny, unbelievably dense center of an atom? For the longest time, it was a total mystery, a complete black box. And today, we're going to crack it open together. You know, our story doesn't begin with some huge, planned-out experiment. Nope. It starts with a quiet, accidental discovery that blew the doors open to a whole new kind of science. All right, picture this. It's Paris, 1896. We've got our first key player, a scientist named Henri Becquerel. Now, he was studying uranium, trying to figure out why it glowed after you exposed it to sunlight. But what he was about to stumble upon was, well, it was something else entirely. And the best part? It was a complete fluke. His setup was super simple, really. He took a uranium compound and set it on a photographic plate. But, and this is the crucial part, the plate was completely wrapped in thick black paper. No light was getting in, period. Then he just stuck the whole thing away in a dark drawer and kind of forgot about it. So later, when he develops that film, he sees something that just shouldn't be possible. There are these dark spots on it, like a picture had been burned into the film right where the uranium had been. That can only mean one thing. Some kind of invisible energy had to have passed straight through the paper. Becquerel had found something brand new. He called it radioactivity. This was the very first clue that atoms weren't these simple, solid little balls everyone imagined. No, something active and really, really powerful was happening deep inside them. So Becquerel basically kicked the door open. It took another 35 years or so, but the next scientist in our story was about to walk right through and find a critical piece of the atomic puzzle. Let's jump ahead to 1932. A guy named James Chadwick is wrestling with this major puzzle. See, whenever scientists would measure the mass of a nucleus, it was always heavier than it should be if it just had protons in it. The math didn't add up. There had to be something else in there, something with mass, but no charge, a ghost particle. And boom, Chadwick found it. At the time, we knew about the positive protons in the nucleus and the negative electrons orbiting around it. Chadwick proved there was a third particle, a neutral one, living right there in the nucleus with the protons. It had no electrical charge. He called it the neutron. Okay, so now we have the key pieces, right? Radioactivity showed us something was going on, and the neutron filled in a huge blank. So now we can finally learn the language, the secret code, if you will, to describe any atomic nucleus in the universe. This next part is the absolute blueprint for everything else we're going to talk about. So seriously, now would be a fantastic time to grab a pen and paper, because once you nail these 3 key numbers, you'll be able to decode any element out there. All right, take a look at this. It's actually really straightforward. First up, you've got the mass number, which we label with an A. This is just the total count of everything inside the nucleus, protons plus neutrons, simple. Next is the atomic number, Z. This one is the atom's identity card. It is simply the number of protons, and it defines the element. And finally, the neutron number, N, which you can find with some easy subtraction. Just take the mass number, A, and subtract the atomic number, Z. So, we've got the theory down. Now for the really cool part. Let's see how scientists take these numbers and turn them into a simple, elegant shorthand to identify any atom in a single glance. This is the universal format right here. X is just the element symbol from the periodic table, like H for hydrogen or C for carbon. The mass number, A, goes on top, and the atomic number, Z, goes on the bottom. So top is total stuff, bottom is just protons. Okay, time to put that pen and paper to work. Let's walk through one together. Imagine we have an atom of cesium. We know it has 55 protons and 78 neutrons. So using the format we just learned, what would its symbol look like? Let's just break it down. Step 1, find the atomic number, Z. Well, that's just the number of protons, right? So that's 55. Easy. Step 2, calculate the mass number, A. That's protons plus neutrons. So we add 55 to 78, and that gives us 133. Now for the last step. We just put it all together. And there it is, mass number 133 on top, atomic number 55 on the bottom, right next to the symbol for cesium, CS. See? Not so tough, right? And that one little notation tells us everything we need to know about the core of that specific atom. Now, this fundamental knowledge didn't just stay in textbooks. Oh no. The very next step in our journey shows how understanding the nucleus led to one of the most powerful technologies ever created by humankind. And that brings us to 1942. Think about this. It's only a decade after Chadwick even discovered the neutron. A physicist named Enrico Fermi used that knowledge to create the first self-sustaining, controlled nuclear chain reaction. This was the breakthrough. This was the moment that really kicked off the atomic age. And this timeline just puts it all into perspective. You can see the whole story unfold, from Becquerel accidentally discovering some invisible force, to Chadwick finding the key particle, and finally to Fermi figuring out how to harness its power. Each discovery was absolutely essential, and each one built directly on the one before it. So what's the big takeaway from all this? After this whole incredible journey of discovery, it all boils down to this incredibly powerful and simple idea. With just two numbers, the mass number and the atomic number, we can describe the heart of almost any atom that exists in the universe. That's just amazing. And with that, I'm going to leave you with a final challenge. We know the formula now, right? Neutrons equals mass number minus atomic number. So how many neutrons are in an atom of uranium-235? You're told its atomic number is 92. Use the simple math we just learned, and you'll have it. Thanks for coming along on this ride, and keep exploring that amazing world hidden inside the atom.